we go. 3 subatomic particles. This is a nice little figure from your textbook that kind of summarizes some important properties of the protons, neutrons, and electrons. So on Wednesday, we talked about this charge, okay? So electrons have a -1 charge, neutrons have a 0 charge, protons have a +1 charge. This right here, AMU, stands for atomic mass units. So you already figure atoms are really small, and so the pieces that make up the atoms are very small. So in order to kind of have any sort of mass that is tangible, there's a new mass on the scene. Okay, not kilograms, not pounds, but atomic mass units. And we'll be talking more about that here to come. So AMU stands for atomic mass units. But check this out. If you were to take a single proton, which has mass, protons are neutrons, electrons, basically the mass is, for our intents and purposes, it's insignificant. Check out how much they weigh in terms of kilograms. So 0.0000, so 26 zeros, and then 167.262 kilograms. So they're very light in terms of kilograms, but in terms of atomic mass units, usually we basically say that both the protons and the neutrons weigh about 1 AMU. Okay, electrons basically don't weigh anything. Okay, so these problems will be due on Monday. He's down there jamming again. So let me go ahead and pull up. These are just some questions about, they're just some questions about subatomic particles like we've been talking about. I had to reboot my computer. To get sound to work. So I think there's 2 problem sets we'll get to. This is or is it 3? I don't know. I'm not fast. Check this out. Is this not adorable or what? See, my sound is not working again. Darn it. I have sound issues this morning. We'll just have to make up our own words. Dogs teaching chemistry. Aren't they adorable? Go back to the show. So this, in physical science, a lot of times we come up with symbols that mean something. So the symbol for the number of protons in the center of an atom is Z, the letter Z. And I'm going to go ahead and kind of put that up here. You guys told me 2 protons is helium. So let's just go ahead and do what the dogs did. And I'm going to go ahead and put these would be my neutrons in the nucleus. And Z, the symbol Z, is equal to the number of protons. And the symbol for proton is a P with a plus. Okay? That's otherwise called the atomic number. Okay? Good with that? Yeah, my Z's, I kind of put a little kind of bow tie in the middle. Okay? And this goes on to say, just like those dogs did, that if your overall atom, I'll go ahead and kind of put a boundary around the nucleus. If your overall atom is going to be neutral, then like they did, the number of protons, which we have 2 in here, this is a helium atom, okay? The number of protons need to be counteracted by the same number of electrons out here. Okay, so there we go, neutral atom. Very good. So the symbol for the number of things in the nucleus, and again, the things in the nucleus are protons and neutrons. The symbol for that actually is A. A is what we call the mass number, but it's not the mass of the atom. Is that weird? Okay, it's the mass number. This is an integer. So an integer is a whole number. So basically, to get the mass number, what you do is you inspect the nucleus and you add number of protons plus number of neutrons. Okay? That's called the mass number. And in this case, of course, as I've drawn this, this would be the mass number is 2 protons plus 2 neutrons. The mass number is 4. Up here, the atomic number is what for this atom?
2.
Atomic number is 2, exactly. Okay, so we're going to get some practice at basically inspecting an atom or thinking about what an atom would look like, and what's its atomic number, number of protons, and what's its mass number, number of protons plus number of neutrons. It's always an integer. All right. So these slides, when I look at them in my office, sometimes I have to read them a few times because I get my atomic number and mass number mixed up, so I just have to kind of focus. This says that the atomic number, which is the number of protons, is unique for an element. That is the number we've been talking about, the whole number that we've been talking about in a box for a given element. Okay. So what's cool is if we wanted to turn this into the next element beyond helium, it's looking like lithium. If we wanted to turn this into a lithium atom, we would have to, via nuclear reaction, squeeze another proton in here. Then we'd have 3 protons. It would have atomic number is equal to 3. It would be another element. Okay. Mass numbers, remember what the mass number is. And this is where I complain because, see, to me, the word atomic number starts with the letter A, but it's the symbol Z, right? The word mass number starts with the letter M, but it's the symbol's the letter A. So I don't know, I don't mean to confuse you, but that's just the way it is. Okay. So the mass number actually can, for a given element, can be different. And we're going to talk a little bit today, just introduce the idea again of isotopes. What an isotope is basically you have the same number of protons, so that says what element it is, but you've squeezed another neutron or so in there, or you've removed a neutron. Okay? And if you do that, you have the same element, but it has a different mass number. Okay? So those are isotopes. So it's possible for the same element to have different mass numbers. Whole number, mass number. Okay, so these are due. Should be pretty easy to pull these up now. 42, 44, 46, 48, and 50. And you know how your textbook is if you're like, I don't know quite how to do that, we'll look at the odd ones.
Those due Monday?
Those will be due Monday too, yeah. So these are just kind of some practice, 42, 44, 46, 48 right here. So you definitely use a periodic table of your choice. Feel free to kind of be using the one like that comes in the back of your notes, because like this is what you're going to have on the test. So if you're one of those that want to kind of, what that's going to be like. So find the atomic number, which will be the number of protons, right, for each of these. And the same thing for 44, okay? 46, you are supposed to go ahead and put the symbol and the atomic number. Kind of some exposure to that. And 48.
Just list the name.
Yep, just list the name. Was it just those four, right?
Oh, and 50.
Okay. Oh, so 50 is a table. Okay, so 50 you're supposed to, for given elements, there's the name, the symbol, and the atomic number. So, you know, feel free. It's good exercise, okay? I almost started to say it feels too easy to get credit for, but it's good. It's good to get you doing that sort of thing. Okay, so isotopes. Okay, if somebody says I have two isotopic forms of the same element, you know that those atoms have the same number of protons in their center, but they differ by the number of neutrons. And that means their mass number differs, but it's the same element. If you've played around with any of those apps that you can download on your devices, mobile devices, for a periodic table, it's really cool because one of the things, pieces of information oftentimes they give for an element is the different isotopes of that element. Maybe not so surprising. Just because you can have different isotopic forms of the same element, and those atoms will behave the same chemically. Okay, when it comes time to forming compounds and chemical reactions, that's more about the electrons than it is anything that's happening in the nucleus. They react the same, but it's possible to, if you have the right tools, it's possible to differentiate between, I think probably using a mass spectrometer, it's possible to differentiate between the two atoms of different number of neutrons, different isotopic forms. So this almost sounds like an oxymoron. It's like some elements only have one isotopic form. It's like, well, if they only have one isotopic form, an isotope by definition is another form of the element with the same number of protons, different number of neutrons. So it seems kind of strange to me. So I've got a slide here to kind of show you, just in general, these only have one isotopic form. So Mother Nature, because of kind of the physics of the atom, actually, the number of neutrons, there's only one option. Okay, so these only have one isotopic form. These have two isotopic forms. Okay. And I didn't bring it with me, but I'll bring it because we'll still be talking about isotopes on Monday. There's all sorts of different tables out there. Okay, these have three isotopic forms, and those have two isotopic forms. These have three or more different kind of versions that these atoms could be, different numbers of neutrons in their nuclei. Okay, so the mass numbers of these would differ from their counterparts. So one other thing I wanted to talk about today is there are times when, even though they're chemically the same, we need to be able to say that the different isotopes of a given element. Okay, so all we need to do basically is say what the mass number is, and then you're set. Because the atomic number actually is given in the symbol, if you think of it that way. If I threw at you the element carbon, you would find carbon on the periodic table. You would see that it has 6 protons in its nucleus. Its atomic number is 6. But somebody would have to kind of clear things up and give you the mass number to tell you which isotope of carbon we're talking about. Okay, so what I'm circling here, this is the mass number. Okay, so that is the number of protons plus neutrons. Okay, and to me, and it doesn't always, this is a little bit redundant, because that's the number of what? What's 6? The number of which subatomic particle? Protons. And you actually could get that from the periodic table. Put another way, okay, somebody has to give you this. You don't get this from the periodic table. Okay, so how many neutrons does this particular atom have in its nucleus? It has 6. How'd you get 6?
Yeah, add protons plus the neutrons, and if it's a carbon 12, then you have to have 6 plus that.
Yep. So you took yeah, exactly. You got it. The difference of those two. So especially that last carbon, that last way to express carbon, we actually call that carbon 12. Carbon 12 has 6 protons in it, but we emphasize the 12 part in carbon 12 to say what the mass number is, because there are different carbon atoms that have different mass numbers. Okay, so that last shorthand notation actually is this, where this, the A stands for not the atomic number, A stands for the mass number, where that is the number of protons plus number of neutrons. And this down here is the atomic number, and that's the number of protons. Okay. So the big number goes on the top, and the lower number goes on the bottom. So that's been done for fluorine. This particular form of fluorine has a mass number of 19, and the atomic number is always going to be 9 for fluorine. Got 9 protons in its center. So what is the atomic number? How many people think it's 19? How many people think it's 9? Okay, good. Very good. What is the mass number? How many people think it's 19? Me too. Very good. Okay. How many protons does it have? How many people think it has 19 protons? How many people think it has 9 protons? You got it. Assuming there's no charge, and I'll tell you, we know there's no charge because later on when we talk about the only reason something becomes charged, here's my atom. The only reason something becomes charged is if it loses electron or gains electrons, okay? This thing is set in stone, so the only thing that can come and go are the electrons. So we know it's no charge because there's nothing up here, okay? That means no charge. Some of you have seen this before. If it had like a -1 or a +1 up there, that means it's charged. All right, so how many people think it has 19 electrons? How many people think it has 9 electrons? Me too. Okay, neutrons. How many people think it has 19 neutrons? How many people think it has 9 neutrons? How many people think it has 10 neutrons? Okay, very good. You got it. Okay, perfect. Okay, so that was fluorine. If we kind of pick on boron atoms side by side, of course, the Christmas red-green thing in the nucleus are the 2 particles, the protons and the neutrons. And we got the electrons buzzing around. This boron has a mass number of 10. This boron has a mass number of 11. Okay, they're both boron atoms. We'd have to look up boron and see that actually on the periodic table it's 5. So it's atomic number 5. So it has 5 protons. And like the slide says, and like you did in the fluorine example, to get to the number of neutrons, you took 10 minus 5. To get 5, to get the number of neutrons for this one, you took 11 minus 5. To get 6 neutrons. Okay. All right. So there's good news here. This is your last set. Okay. The good news is you're not doing 85 and 86 because we haven't talked about charges yet. So just those 3, 88, 90, and 92. And actually those do go back to being kind of a table. I'll show you what they look like. There we go. Okay. 88. I guess they aren't tables. The ones that were table I pulled. So just these, no table. So 88 says how many neutrons are there if, for instance, you have an atomic number. Z is the atomic number, and A is the mass number. Okay. So of course, to get neutrons, we're gonna subtract
the mass number
exactly.
by the.
For 90.
28.
Let's just do the first one for 90A for an example.
We're only gonna do A for 90?
No, you're going to do A through D, but let's do
Oh.
A together.
Oh, okay.
Yep. So A looks like this for iodine. The symbol for iodine, I bet you would tell me, is I. Okay? And then what you're supposed to do is basically put these two numbers up here. The big number goes in the upper left-hand corner. The small number goes in the lower left-hand corner. The top number must be the mass number, right? And they're telling us it's got 74 neutrons. How are we going to get the mass number? First off, tell me what number goes down here. What's the atomic number? I'd have to look at the periodic table. 53. Does that, everybody buy that? So I'm going to put 53 in there. I like that.
There's that 53 and 74.
What's that?
Now you just add 53.
Yep. Now you just add 53 plus 74. That seems pretty big, but yeah.
27.
What is it? I'd have to go over here. I'd have to give my calculator. 72, 53, 5. Yep. Does that look right?
No, you did
No.
72. It's 74,
Oh,
so it's
thank you.
127.
Good job. Thank you. Very good. Does that work for you? Perfect. That's a lot of neutrons. And wasn't iodine one of those kind of weird ones that you found on your periodic table yesterday? It basically came after tellurium, okay, but it was heavier. Or sorry, tellurium was heavier. So
Wait,
anyway.
don't they want this for 92? Because it says write the symbol of each isotope like that, but they're not there. They want it written like,
Oh, that's true.
yeah.
Yeah.
So if
Yeah,
they,
you're
they
right.
want that for 92.
Oh, thanks, Cameron. What Cameron is saying, and he's right, is actually, I would take either at this point because I feel like
Okay.
I've confused the matter. But he's right. Really, the form they're wanting is this, I dash, and you guys told me 127. That's the form they're wanting for here. Thank you. And then down here, it's the form like I did. Good, very good. Okay. Clear as mud? Was that just three little ones? And we're going to go ahead and quit for the day. Bring your calculators Monday. Yep, because we're going to talk about that decimal number, how much atoms weigh.
What time,